Convexity Theory Part 2 will be differentiable functions and optima. So what we shall look at here is gradient and Hessian of a n-dimensional function, Taylor's series expansion of the function, convexity property from gradient, then convexity from Hessian, local and global optima, and finally, necessary and sufficient conditions for optimality. Given a function f which maps an n-dimensional point to a scalar, the gradient del f of x is also an n-dimensional vector whose ith component is partial f of x over partial x sub I. And therefore, del f of x is this vector. Its first element is partial f over partial x1, and the next element is partial x over partial x2, and the last one is partial f over partial xn. This x here is x1, x2 until xn. Consider a Euclidean plane function f of xy defined on two variables, x and y. And so x is, this vector x is comprised of two scalars, x and y. I use bold straight for vectors, and for scalars I use non-bold italics. And f of x is a scalar, so f of x belongs to R. So I take the domain of the function, which is shown below here, and then I take its top view, which is this on the left. The gradient del f of x given a point x is this arrow, and look at the function. The minimum of the function is here. The gradient is pointing away from the minimum. And if we look at the top view, this is the gradient of the function. And now these circles are called level sets, and they represent f of x equals constant. So this minimum by itself is one level set. This circle is another level set representing some value of the constant, and this circle is yet another level set. And as we go further and further away from the minimum, the value of the constant increases. But everywhere along, if you look at any circle here, the value of the function throughout that circle, that level set, is fixed. It's a constant. And this is del f of x, which is the gradient at this point. In this illustration, the minimum of a function is this black dot here, and these contours are the level sets. The blue arrows are the directions of the gradients. And let's look at this point here, x. Del f of x is the gradient. Now, if we want to increase the function, we can go along this direction, we can go along this direction, we can go along this direction, we can go along this direction. There are so many directions we can go along to increase the function. But the direction of steepest ascent of the function is the gradient. So the gradient gives the direction of steepest ascent of the function. The gradients are orthogonal to the level set. So this blue arrow here is orthogonal to this level set at the point x. This blue arrow, this gradient, is orthogonal to this level set at this point here, and so on. And the level sets are f of x is constant. Everywhere here in this level set, the value of the function is some constant. It's some other constant here, and it's yet another value here, and so on. Given a function from n-dimensional Euclidean space to a scalar, del square f is the Hessian of a function, and it is a matrix whose element in the ith row and jth column is partial square f over partial xi partial xj, which is the same as partial square f over partial xj partial xi. So the order of differentiation doesn't matter. So del square f, the Hessian, looks like this big matrix here. The diagonal elements are partial square f over partial x1 square, partial square f over partial x2 square, until partial square f over partial xn square. Now, the non-diagonal elements, given this property here, since the order of differentiation doesn't matter, the non-diagonal elements are such that this Hessian is symmetric. For instance, del square f over del xn del x1 is equal to del square f over del x1 del xn. Taylor series expansion of a function f x plus delta x is the Taylor series expansion of the function f around x, and delta x is a small perturbation. It's equal to f of x plus summation I of partial f over partial xi times delta xi. This is the sum of all first order terms, the first derivatives times perturbations, plus half of summation I, summation j of the second derivatives, partial square f over partial xi partial xj times the perturbations delta xi delta xj. Remember that x here is a vector and its ith component is xi. So each of these xi's are the ith components, and likewise for xj. And delta x is also a vector whose ith component is delta xi. So this is the Taylor series expansion of the function, and I've only written down the up to the quadratic term, and then cubic and higher order terms are not shown here. More concisely, fx plus delta x can be written as fx plus gradient del f of x transpose delta x, where this is the vector and this is half delta x transpose times the Hessian times delta x, and this is all higher order terms. I've clubbed them together, and this is the error produced by the higher order terms, and its order delta x cubed. Dropping the error term, we can write fx plus delta x is approximately equal to this. So this is a quadratic approximation of the function f around x. F of x plus gradient times delta x plus half delta x transpose Hessian times delta x. If y equals x plus delta x, we can rewrite Taylor series approximation in this form. And this is the quadratic approximation where we are dropping all the higher order terms. We've seen what a convex function is. It must obey this property. F of a convex combination of 2 points should be less than equal to the convex combinations of the f's of those 2 points. Graphically, this is what it looks like. I have 2 points, x and y, and so this is the convex combination theta x plus 1 minus theta y, and this is f of theta x plus 1 minus theta y, which is the left of this inequality. And if I draw a straight line like this and get theta f of x plus 1 minus theta f of y, that's the convex combination of the values of the function f of x and f of y, I get this side of the inequality. And if it's a convex function, then this straight line joining x and y must lie above the plot of the function itself. Convexity of a differentiable function. So now let's take 2 points x and y, and since we are looking at a differentiable function, we can define convexity in terms of the function's gradient. So f of x plus gradient del f of x transpose times y minus x must be less than equal to f of y. That's a property of a convex function. So here's a function in one dimension, f. What's shown in this figure is the plot of the function. This is the x-axis, the value of the independent variable, and on the y-axis is the function of that variable. This is the plot of that function. Let's take a point x and mark f of x, and take another point y and mark f of y along the y-axis. I draw a tangent to the function at this point x. So this red line here is a tangent to this function at the point x. And obviously, the slope of the tangent is equal to the derivative of the function at that point, which is partial over partial x of f of x. From geometry, from here to the height of this line segment, from here to this point here, is f of x plus slope, this is the slope, times y minus x. And that's what appears on the left side of this inequality. And on the right side, I have f of y. So for the function to be convex, this property must hold. F of x plus slope at point x times y minus x should be less than equal to f of y. In other words, the tangent should always lie below the function for the function to be convex. If the function, for instance, if the function were like this and it moved down and then went up again, then the tangent would not lie above the function, below the function everywhere, and so that would make the function non-convex. Convexity of twice differentiable function. Since we are looking at a twice differentiable function, we can define the Hessian, and so now let's look at convexity in terms of the Hessian. At every point x in the domain of the function f, if the function is convex, then the Hessian del square f should be positive semi-definite, and if the function is strictly convex, then the Hessian should be positive definite. By positive semi-definite, we mean that all the eigenvalues of the matrix should be greater than or equal to 0. And by positive definite, we mean that all the eigenvalues of the matrix should be strictly positive. Now let's move on to minima of a function. X star is a local minimum of f of x if there exists a ball B with center x star, which is this point x star, and with radius r, an arbitrary radius, such that if you take any point x lying inside the ball, then f of x star is always going to be less than equal to f of x. That is, within the ball, you cannot get lower than f of x star. Then x star is a local minimum. In this figure here, this is the point x star, the local minimum, and so this blue sphere here is a ball of radius r with center at x star. Everywhere in this ball, the value of the function will never be lower than that of f of x star. In other words, this is the smallest value that the function can get. X star is a strict local minimum of f of x if this less than equal is replaced with a strict inequality, strictly less than sign. So you take any ball, any point x in the ball, f of x star is always going to be strictly less than f of x. That's the condition for x star to be a strict local minimum. Now, instead of confining ourselves to a ball around the minimum x star, if we consider the entire domain of the function, if x star is the smallest value of the function in its entire domain, then x star is a global minimum. In this illustration here, this is a local minimum, y star. So it's a minimum of, if we take this line segment, if we assume this to be one-dimensional, then ball would be no more than a straight line segment. So if you take a straight line segment around y star, then y star is, as you can see here, it's the lowest value of the function in that ball. Therefore, it's a local minimum. And x star here is a global minimum because nowhere is the value of the function lower than f of x star. Minima of a convex function. So now let's focus on a convex function. For a convex function, every convex function has a global minimum. And every local minimum is also a global minimum of the convex function. So this is a plot of a convex function, f of x. And any point in this horizontal line segment is a global minimum of the function. Minimum of a strictly convex function. Every strictly convex function has a unique global minimum. In the previous slide, the entire horizontal line segment was contained the minimum points, but in a strictly convex function, you only have a unique point, which is the global minimum. So this is a strictly convex function, and this is its unique global minimum. What are the necessary and sufficient conditions for a minima? So we will focus on twice differentiable functions so that we can define the gradient and the Hessian. Is the point x star a strict local minimum of the function f? A necessary condition is that the gradient at the point x star, which is del f of x star, must be equal to 0. This is the vector analogy of a scalar function, f of x. The derivative, the first derivative, must be equal to 0 at the minimum or the maximum. Second order necessary condition is that the Hessian del square f of x star must be positive semi-definite. And a sufficient condition is that del square f of x star, the Hessian, must be positive definite. And this can be easily seen from the Taylor series approximation of the function around x star, where delta x is a small perturbation. Now, from the first order necessary condition, this is the first. This term contains the gradient. It becomes equal to 0, and so what we are left with is this as our quadratic approximation. It has f of x star, and this is the Hessian term. This is the Hessian, and this, for x star to be a minimum, this term must be positive, which implies that del square f of x star must be positive definite. So that f of x star plus delta x is greater than f of x star. That's why x star is a strict local minimum. Now let's look at some other situations for the Hessian. What if the Hessian del square of x star is negative definite? Then x star is a strict local maximum. What if del square of x star, the Hessian, is not positive definite but positive semi-definite? In that case, x is a local minimum but not a strict local minimum. What if del square f of x star is indefinite? In other words, the Hessian has positive and negative eigenvalues. In this case, x star is a saddle point. A saddle point looks like this. So in this figure here, this red dot you see, that's a saddle point. It's a minimum along this axis, but along this axis, it's a maximum. So minimum along this axis, maximum along this axis. That's why x star is a saddle point. What if del square f of x star is equal to 0? In this case, we cannot say anything about x star. Now, remember that this condition that the Hessian be positive definite is a sufficient condition. It's not necessary. In other words, if this condition is not satisfied, well, this condition must be satisfied. The gradient should be equal to 0 at x star, but even if this condition is not satisfied, it does not mean that it's not a local minimum. X star could still be a local minimum, as this example shows. So f of x is x to the power of 4. The strict global minimum is x star equals 0. The gradient del f of x star is 4x cubed, which is obviously 0 when x is 0. And the second derivative, del square f of x, is actually 0. But we know that x star equals 0 is a strict global minimum. Here, this sufficient condition is not being satisfied, but it still is a strict global minimum. Now, what about a convex function? We know that a convex function has a global minimum, and a local minimum is also a global minimum. And especially, we know that for a strictly convex function, there is a unique global minimum. If f of x is convex and differentiable, then is x star a global minimum? A necessary and sufficient condition is that the first derivative, the gradient, must be equal to 0. If this condition is satisfied, we don't even have to look at the Hessian. This condition being satisfied is enough for x star to be a global minimum of the convex function.